Hi, good afternoon, everyone. Thank you for joining today's DBMI seminar. It's my great pleasure to introduce our speaker today. Dr. Jay Yang is an assistant professor at Harvard Medical School and a lead investigator at Brigham Women's Hospital. He has extensive expertise in medical informatics, AI in healthcare, and clinical NLP. Dr. Yang is an elected fellow of American Medical Informatics Association and also affiliated faculty member at the Broad Institute of MIT and Harvard, and the Harvard Data Science Initiative, and also the Kepner Institute of Harvard University. He serves on the technology advisory group for the World Health Organization Global Clinical Platform. His research focused on developing and applying advanced AI and NLP methods, and he has also won many awards including the Best Paper Award at Colin and Best Demonstration Paper nomination at ACL, the top NLP conference. And he's also associate editor and guest editor of NPJ Digital Medicine, and also associate editor at IEEE Transactions on Neural Networks and Learning Health Systems. So it's my great pleasure to welcome Dr. Yang, and then today he's going to talk about his recent research on large-scale multilingual evaluation of large language models on real-world clinical data. So without further ado, Dr. Yang, please take it from here.
Thank you very much, Professor Wen. Thank you very much for this great invitation. And can you see my screen correctly now?
Very well, and we hear you
Okay.
very well. Mm.
Okay, great. Thank you very much. Yeah. So yeah, it's great honor to be here to give you a kind of introduction about our recent work. So Columbia is a special to me. The Columbia is my PhD postdoc supervisor, Professor Lee Zhou's original institute. So I see a lot of kind of big names from Columbia University. It's a great honor to be here to present our recent work. So today's talk is talk about the large-scale multilingual evaluation of large language model on real-world clinical data. So I'll give you a very kind of brief introduction about the background, why we are going to explore this direction, and that give you kind of a whole overview of how the process of our work, and we have several follow-up studies that go deeper into this evaluation studies. So the basic background of this topic is that we see a lot of kind of good news and headlines from news or top journals that see national language model have demonstrated very strong capability in healthcare in clinical settings. So in the left figure is a quite typical image that shows those kind of national language model have demonstrated very good performance on the United Medical exam, the USMLE task. And such as at the beginning, the GPT 3.5, when the ChatGPT comes out, there's many headlines show that okay, ChatGPT has passed. They have get the score of 60 at USMLE exam, and they have a news show. Okay, ChatGPT can pass the medical exam, can replace doctor. There's a lot of discussion about that. And then this kind of evaluation, this kind of benchmark has been quickly being satirized. So there's a Google several model have reached to 86, and they have GPT-4 and new models comes out. So they are currently those new advanced model have reached easily reach over the 90% of these medical exam tasks. And there's I think have a news from Open Evidence or other kind of startup companies that even claim their model can reach 100% in this USMLE exams. So it sounds like this kind of task having is kind of a solved problem for USME and shows them have a very good performance kind of healthcare. And the rest, the right figure is just a paper published maybe 2 weeks ago in Science, and a group of physicians and scientists can evaluate the performance of with the physicians and different versions of and compare the national model with physician. So they just compare with on course different kind of tasks. So this figure just shows them on diagnosis task. So they compare the different versions of ChatGPT and also have a GPT-4 plus physician and physician only. And before I look at the paper, this common feeling is that okay, so maybe the AI is better than physician, but AI plus physician can be will be the best performance. But this one is different. The performance shows that with physician with some kind of access to resources, the problem is the worst physician plus GPT model or even lower, the performance even lower than GPT only. That means that with many cases, for diagnosed cases, those physician plus GPT can make performance even worse. The GPT-4 can give a good prediction, but with the physician working together, the performance even can get worse. So that gives us some kind of surprise that okay, our large model is quite good on this kind of different kind of task, and they are a very good performance. But on the other hand, we also see different kind of studies that show those kind of diagnosis is not that well on medical tasks. Such as this paper come from the New York Journal AI, and they evaluate the large language models on the medical codes, just giving this kind of EHR notes and to do the code automatic coding. And the performance shows that is quite poor for medical coder. So here, such as some ICD-10, so give them exact max performance actually is quite low. It's around 20% of this kind of evaluation. So their conclusion is that are poor medical coders. The performance is not that high. It's have a very limited performance. And another study come from German pediatrics. They have explored 100 questions about the pediatric questions and then ask to answer, but they've identified 83% of this kind of cases, pediatric cases have make errors. So it's a very, very high error rate on those kind of tasks. So the things that the existing study has shown inconsistent regional performance across different kind of applications. So as a user, as a even a developer or physician, they want to choose their own kind of large language model. The common question is that when and which perform the best on my own applications. And how good, how bad this kind of performance is. So they have a kind of common needs, but we see the different kind of inconsistent performance. And so it's kind of just give us another confusion on how can we choose this kind of model. And on the other hand, that we see this evolve very rapidly. They have almost there's one new model released every week, even one every day. They have new model release. So it's a large number of new model comes out. We don't know how good or how bad this kind of new model on our specific medical applications. So it is really important to build the benchmarks to assess those advanced in medicine, and also we want to track this kind of new release model. Not only just we publish paper, we get the performance of GB3.5, GB4, which one is better? But the currently when we currently use the model, they have new versions. We don't know how good this kind of new model. So we want to track the new release models. So they do have a lot of kind of benchmarks for LLM on medicine applications, such as the common is the MediQA, which include different kind of medical exam, including the USMLE, and also have PubMed QA that's just using giving PubMed abstract and give a specific question binary questions, and also have many other kind of medical exam questions. Health branches come from OpenAI. They have a build a big group of experts to create different kind of clinical scenarios. And MMLU is a commonly it was a commonly used not general national evaluation benchmark. They also include subset of medical related subsets. And the benchmark of biomedicine also was a benchmark which will also use PubMed and other kind of dataset. So those are open kind of benchmarks, and they also have other kind of a lot of other studies, such as isolated evaluation of specific clinical scenarios, such as the paper we mentioned in the science paper we mentioned before, and also many other kind of papers that they evaluate on specific application scenarios, and they evaluate several and conduct this kind of comparison. But the problem of those existing kind of benchmark is that, such as the medical exams, those kind of QA kind of question settings, benchmarks, they just overly simplify the task, and they do not reflect national performance in real world clinical understanding. Those kind of USME, they just give you a kind of assume a scenario, and with 4 or 5 options, you can choose from them. And but in reality, they don't have those kind of options for you to choose. And also the text, those kind of questions, they have a well defined, they have grammar correctly without any specific kind of aggregation and grammar errors, those kind of things, which has commonly occurs in the real clinical scenario. And the isolated clinical evaluation, there are a series of studies evaluate kind of performance on specific scenarios, they are not comprehensive, and they want to. It's hard to generalize, such as okay, I see the have good or bad performance on the pediatric settings on specific hospital, but we don't know how good or those conclusions can be generated to a specific application. In my opinion, among working on elderly patients and on the different hospital, the conclusion is hard to generalize to different scenarios. So there is a lack of dynamic kind of benchmark for on diverse real-world clinical tasks. And with the new model comes to continue to emerge, we want to include those kind of new merge to evaluate those kind of so the general background of the settings that there is a need for benchmark to benchmark and evaluate state-of-the-art large language model, and specifically we want to have several additional kind of features. First is that I want to focus on real-world clinical data, especially in the EHR, electronic health record data, because those kind of text EHR knows those kind of data. They have include a large number of patient healthcare related information, those clinical status, history, procedure, they all documented in EHR notes. And for physician, the clinical decisions are based on the EHR data in practice. So those are really close to the real clinical decisions. And also those real world clinical texts, they are messy. The format is totally different than what we see from the general medical exam or the Wikipedia or those kind of PubMed data, which are well written. But those kind of real EHR text is totally messy and it's bring much more challenge for to understand this type of text. And another several kind of other several kind of career we want to include is that there are not all kind of evaluation are focused on English, and we want to include more yeah, languages to make it the conclusion on our observation on different kind of language observations. And also we want to include large scale. We want to try to make our kind of conclusion generalizable, can generate different kind of application scenarios. So we include large scale of data and also include quite diverse tasks. So those are the in terms of the benchmark design. And also for LLM, we want include much more kind of, rather than the state of art, just several state of art model. So it's the open source model, commercial model, that different kind of needs for commercial open source model, and also medical model is a lot of fine-tuned model for medical usage, and medical model and general model, and also a small versus large model, different kind of hospital or clinical scenarios. They may have different kind of infrastructure. They may don't have too many GPUs to host those kind of big models. So they need to make their own trade-off balance between the performance and the model scale. So we want to provide a more comprehensive evaluation across different kind of settings of candidates. So that we want to include kind of different kind of type. And also we hope to have this kind of open leaderboard. So for each user they want to use, they can just click and select based on their own kind of needs, such as we want to select the model less than 40 billings, and also have the best performance on Germany and have a best performance on summarization tasks, kind of things. So they can use this kind of open leaderboard to select their own kind of application scenarios to choose the best model they want. So those will go into our we call bridge, the benchmark large language model for understanding real world clinical practice text. And so the general setting of the bridge is that we actually include 87 tasks based on real world EHR data, and collected globally. We are not just focused on one or specific kind of institution, we just kind of connect those kind of data globally, and we evaluate. So here we just show the 95 LLMs, and we'll just keep updating. Now we have included 107 LLMs, includes advanced models. And all the experiments are conducted on HIPAA compliance environment. So even some kind of data such as Mimic, right? Although they can be accessed, but they have a specific data user agreement. We cannot upload this kind of data directly through the OpenAI, this kind of API, this kind of website. We will only run this experiment with MGB, Mass General Brigham HIPAA compliance environment to follow the data user agreement. And those are some characteristics of the whole and distribution of the task. So we, in terms of tasks, here type of task will mean the natural language processing task. So you can look at the right corner figures. So we have include 8 different kind of natural language processing tasks, such as task classification, some classification tasks, the ICD codes, kind of things, event extraction, and then we can just extract some kind of specific concept from the EHR nodes. Normalization and coding is also something like the coding and the summarization, etc. We have 8 different kind of tasks, and also it cover multiple kind of a lot of kind of different clinical applications. And we run large number of experiments. We have more than 24,000 experiments with actually now it's more than 40 millions of LLM inference. We have built a very large scale of evaluation settings. And it covers 9 languages. It's covered with English, Chinese, Spanish, and top language. So we will ensure for each language it will include at least 3 different kind of tasks to ensure this kind of stability of the evaluation. And here is the leaderboard we show. You can just select different kind of settings. You can select the commercial general medical open source commercial model or model size. And in the down, we didn't show the full kind of page, but in the down they have a more kind of fine-grained settings to field, language, applications or settings, and you will see under specific kind of choice you have which model perform the best. And here we'll just introduce how do we build this kind of benchmarks, and also we'll introduce some interesting kind of findings we during our experiment when we explore this kind of different kind of model performance, and also we have some kind of further in-depth analysis of some model performance. So here is the basic of this kind of benchmarks come from our previous paper, which have been published in General AI, and we connect 192 real-world clinical datasets and identify and find more than 3,000 papers. So we just do the literature reviews. Those are before the ChatGPT when we connect this kind of data, so the fully manual work. So we do this kind of review to search more than 3,000 papers and identify them if they include some kind of any kind of real-world clinical data that can be shared, or and then we in the end will find or do duplication or different kind of settings, and we find 192 unique data sets. They are all from real world clinical data sets, and then all those papers just claim that the data can be accessed through either they are fully accessible or the majority of them just can through reasonable request. So we send an email to those kind of groups and multiple times and request kind of data through reasonable request. And if they do not respond, we have a very strict kind of pipeline. So if they do not respond in 3 weeks, we'll send another email for all the first author, last author, and all the author list, and do step by step. And in the end, we include 91 dataset that are accessible. We can get this kind of data, and the 14 dataset is the regulated data. We can still get the data, but they have do some kind of regulated data use agreement is kind of signed, but we can't get this kind of data. And the 87 data are inaccessible. We cannot get this kind of data. Even those paper claim this can be accessed with reasonable request, but still cannot get this kind of data. But at least we have a very good kind of base around more than 100 data sets that we can use. And for this study, the benchmark, the bridge benchmark, we have also include more data sets because such as the Hugging Face, we have include more search data from more sources, such as the Hugging Face, which has been commonly used on the data sharing platform and model sharing platform during national language area, and also SciNate as also a wide famous kind of clinical data sharing platform. So we search, do another round of search and add more data to the our existing benchmark, and then we do a filtering. So we will not include all the data that are available in our group. We just do another filter, such as we'll ensure the evaluation sample should be more than 200 samples to ensure that the assessment is robotic. And the language for the language we include each language should include at least 3 tasks, and all this kind of data, the text should come from the real world clinical text, and the task should be clinical relevant. So in the end, we have included those 87 tasks and with 9 languages. So for each model and each task, this kind of combination, we have tried three different kind of assess three different kind of inference strategies. So the zero shot, few shot, and the channel shot. The zero shot, I mean, we just give them kind of questions and ask them to give the answer directly. Few shot, we will for each question will give them five random selected examples and then ask them to give the final prediction. And the suit is that we do not ask them to do prediction, the answer directly, but ask them to do the think them first, think step by step, and then do the prediction or answers. So there are three different kind of inference settings. So we for each kind of task, we have designed different kind of specific kind of evaluation method and metrics. And so such as for the simulation, we have used some kind of burst score. For the NER memorization, we use an F1 measure. For classification, we use accuracy, etc. We customize the metric and methods in terms of different kind of NLP tasks. So the model we have evaluated includes advanced multiple CR1, GPT-4, Gemini. We're currently also trying to evaluate the GPT-5 and Gemini GPT OSS and all those open source models such as GPT OSS, Llama 4, etc. And we have for this 95 model, we include five proprietary models and 17 medical specific models and 17 reasoning models. And the model size is quite diverse. We run the model from 1 billion small model to 671 billion. That's the DeepSeek R1 model. And this also for the open source. For the proprietary model, we don't know the model size, but we run through them through their API, HIPAA compliance API, to run those experiments. So we just have a very large coverage of the model size and the model characteristics. So here we go some kind of interesting result we find. So this one is the general performance of the those are the y-axis is the aggregation or performance of all kind of tasks, all 87 tasks, and for x-axis represent the time of the model release, and the red dot represent the proprietary model. The rest of the model have represent the fine-grained open source model. But the general kind of trend we can see is that at the January 2024, the GPT 3.5 top is have a very huge gap between those proprietary model with open source model. That's the Llama 2 70 billion models that actually have a very huge gap between this kind of model. But with time goes, those open source models have quickly approaching to the proprietary model. The difference is quite minor. And during the January 2025, the DeepSeek R1 was the best model of all the models. So it's even better. So open source is even better than the proprietary model. And with the one that Gemini 2.5 Flash release, they have a kind of a proprietary model can go back to the first pace of the model form. But we see those kind of difference getting closer and closer. And here is the more kind of fine-grained performance with some top perform models and all some typical models. So each model have we have evaluated 12 here we just need 12 different kind of models. The top performance or quite typical model, and each model will have three bars. The first bar represents the zero shot, just ask them to do the prediction directly. The second represents the COT, just the thinking first, and then to give the answer. The third one represents the few shot with five examples first, and then to the answer. So we can see those kind of models in terms of those kind of zero shot settings. The first bar of each model, the Gemini 2.5 Flash, DeepSeek R1, GPT-4, and Queen 3 Next, thinking model are the top four LLM models. They have two proprietary model and two open source model. And in terms of five-shot inference, at that time, the Gemini 1.5 Pro is be here perform the best on the five-shot inference. But the one interesting observation we see is that for if we compare the few shot with zero shot, we see this kind of give them five examples can significantly improve the model performance. We see the always have a very large kind of improvement compared with the zero shot and the five shot. And if we compare some kind of open source model, even limited size of open source model, such as here, Metagamma 27 billion will be here. If you give it with 5 examples, the performance is around 52, which already largely beats those kind of state-of-art commercial model without any kind of example. So those be giving the model from with several examples will be a very cost-effective way to improve the model performance. But another interesting thing we observed is that for the second bar, so almost all the models that the second bar has the lower performance compared with the zero shot. I mean, zero shot COT channel shot decrease performance model in those kind of medical tasks compared with the zero shot. So we will have a separate exploration for the reason why this kind of COT decrease model performance. We'll explore them then later. It will be an interesting and also relatively consistent observation from the large-scale experiment. And here we compare the model performance across different kind of NLP tasks because the previous figure just average all the performance across the different tasks, and here we'll give a more fair or fine-grained comparison with different kind of model task across different model. So each figure represents a specific NLP tasks. So language recognition, task classification, coding, summarization, etc. So the general setting is that we can see the LM generally does not perform very well on those kind of tasks. So even the best performance, such as natural language inference, will be binary prediction tasks. The performance is relatively good, 87, best maybe 87 percent of accuracy. But those are is a very simple kind of task for binary prediction. But for the rest of the model, they are not show very good performance. And they may have a reasonable performance on text classification tasks. Over here, the best model have around 70%. But for the performance on NER, such as name recognition, the best model even only have less than 50% F1. These are all the zero shot settings. Only have a 50% of F1 score on this kind of NER task. If we compare the LM performance on general domain NER task, such as which is one of the commonly used data we call Corner 2003. It's relatively old, but has been quite popular use. The performance can easily reach more than 93% of F1 score. But here for medical NER tasks, they only have less than 50%. So they have the performance is not satisfactory and have a significant large drop compared with the general settings. Specific for those kind of normalization and coding tasks, that including the tasks that have given a notes and use them to do the ICD coding, the performance is pretty low. So the best performance is DeepSeek R1 is only less than 10% performance. But this will be the observations are quite consistent with the previous study we see from New England Journal of AI paper. They have also showed that LLMs are poor coders, and we also see this consistent result in our experiment. And here we have some kind of performance comparison on a different language. So because different kind of language here, such as Germany, English, the different kind of language include different kind of tasks. So we cannot compare that. Okay, the LM is better than English and than German. We cannot compare performance across language, but within each language, we can compare more different kind of models. So here we can see the Gemini 2.5 Flash is the best in Chinese, Spanish, and German. Germany, GPT-4 is better in Norwegian, Japanese, DeepSeek R1 better in Russian, German, and etc. So we can see on each kind of language which model perform the best. But those are all aggregate all the performance on all the tasks within a specific language. So if you have one interesting about NER task in German, you have a maybe more fine-grained evaluation. The ranking may be different. Here the figure we have a left and right figure. So the left represents the general domain LLM, and the right represents the medical specific LLM, and they are all in the same scale. So we can compare them from left to right. Directly, so the common feeling is that the general domain LLM is better than medical specific LLM. So we see this kind of performance is more kind of cover more area compared with the right figure. So it's also been been seen in many kind of experiments. But on general is better because one reason why guessing that those kind of medical specific they're fine tuning on normally fine tuning on the older version of LLM when they train and release this kind of big companies that already released the next version which is much more powerful than the old version. So this also be a potential reason that why the medical model is less performance than a general model. So scanning noise is also another interesting exploration we see. It's commonly has been commonly proves that with bigger models, the model have generally have a better performance. So we expose kind of scanner whether those scanner also holds the medical tasks when they apply to medical tasks. So we choose four typical model families: DeepSeek Llama, Queen, and MiNAMA, and with different kind of model size, and which also realize different under different kind of influence are those kind of scanner still hold. So you can see those kind of trends are quite clear, right? With all these kind of inferior settings, the bigger model normally have a better performance compared with small model. So it's also still hold in the medical application. And so those are the basic kind of very surface kind of statistics and the result we see. But we also want to explore some in-depth analysis, such as the one thing we have explored that why the COT fails in the real world medical data. So it's having when the COT was proposed, they have been demonstrated that it's normally will have improved the model performance of the generals, especially for the mass calculation have the better performance, will improve the performance over the usual settings. But here for medical settings, we see that most of them are just have a worse performance compared with the COT. So we want to explore why this happened and why it's kind of quite consistent across different model and different kind of tasks. So we have a detailed analysis and exploration on the reason why it fails. And another analysis is that because we already run this kind of experiment, we want to utilize understand that the LM will generate all many kind of when they understand those EHR tags, they'll generate another kind of analysis of those kind of tags. Those kind of tags or reasoning tags include some kind of stigma language, I mean the offensive language to patients, which has been coming with a kind of popular topic in the many EHR studies. The researchers want to explore that is EHR has been include many kind of stigma offensive language to patients. But here, the LM output may also include kind of stigma language. So we want to explore the kind of distribution of the stigma language. So we have two further analysis. So the first one, we go to the COT fails. Why the COT fails? We are very curious about the observation. This performance is consistent and not all performance have been of the COT performance drop, but the majority we have maybe around 85, 86 of percent of the model have the performance drop with COT settings. So here we just realize the direct comparison between COT and the zero shot. We see the majority of them have a performance drop with COT settings. So we have this will be the workflow for how we explore the COT fails. So the basic, the beginning will be the same other experiment. We have a more different kind of tasks and different kind of models, and then we have a further kind of analysis. So here we have a multiple kind of, analysis on the reason. So first is the performance comparison. Maybe with different kind of model performance, what's the difference between the COT and the zero shot? And the second is the reasoning length. Maybe what the performance drop may also related to the reasoning length. The COT length is the longer, the performance drop may be even bigger or smaller when we expose correlation between these two. And the medical concept alignment will also explore with the input and and output kind of text. Those kind of medical terms mentioned by have kind of more the alignment between the input and output of medical terms. Those kind of alignment value will be related to the performance drop. And also want to analyze some lexical difference analysis for the COT failed and COT success cases. What are the lexical difference? Some words are more frequent than the COT success cases. Some words are more frequent than COT failed cases. So also have error analysis, the more direct analysis. We using large number of George and have expert review and to explore what's the distribution of the errors of COT. So we do not we will not introduce all the analysis, but just pick some of interesting analysis we find in our analysis. So the first one is that the model performance. So we because we have run over 95 models. So group the model performance across based on the performance, such as the figure shows that top 20 model means that we rank the model based on the performance from top to down. We pick the top 20% of performing model. They are the best 20% of models and aggregate them together and compare their COT and zero shot performance. And then we group them into the model into 5 different groups based on the performance, 20% to 40%, 40% to 60%, etc. And then for each group, we measure the difference between the COT and the zero shot. We can see the curve here is quite interesting. With the top perform model, if the model have a better performance, the drop, they still have a drop because you have a negative value here. They still have a drop, but the drop is smaller between this kind of COT and the zero shot. But with the model getting worse and worse, the drop, we will use COT settings, the performance drop will kind of getting bigger. So that'll be very interesting observation. Maybe the worst model have when they do the multiple step reasoning, they're more easy to get error propagation. Such as one step have an error reasoning and then error will propagate to the rest of things, and much easier for them to get this kind of um, uh, correct prediction in the end of the COT settings. And another experiment is that we compare the COT drop with this the reading length. So the COT length we have they have different lengths. We just want to compare what's the performance between this length and the reading length and the performance drop. So here we picked 4 typical models: GPT-4, MiNAMA, Queen, and NAMA. And this one is proprietary. The rest of 3 are open source, and we also include this one medical service. But we see if we compare this kind of different across the reasoning lengths, we can see with these it's quite common that with the reasoning lengths getting longer, the problem drop here, the problem drop can given higher. So it's be we only see this kind of associated, but we do not we cannot explain why it's coming. But it'll be an interesting observation based on this kind of experiment analysis. Maybe one of the reasons is that with a longer kind of reasoning length, the task will be even harder, and for the harder task, if you use the COD settings, it may be much easier for get error propagation for this kind of setting. We will not confirm this kind of reason, but it's be a guess. But we are ongoing project to explore why this can happen, what the relation means between the reason length and the performance drop. And another thing I want to share is that we do the lexical analysis. Just we group them all the experiments and pick the cases into categories into 2 groups. One group means that COT success cases. The zero prediction have wrong prediction, and COT have the correct prediction. So that we call COT success cases group. And another is the COT failed cases. For the zero shot prediction is correct, but COT has incorrect. So group those 2 kind of group output and then analyzing the text distribution, the lexical distribution between these 2 groups. And they were very nice in this kind of figure, scatter figure. So here the x-axis represent the word frequency under the COT failed groups, and the y-axis represent the word frequency under the COT success figures. So here, such as for the top left, right, those kind of dots, those kind of words represent those words have very high frequency in the COT success cases, but have a very low frequency under COT failed cases. So you can see this kind of for the down right corner, those kind of figure will represent the COT have those kind of words have very high frequency under the failed cases, but have low frequency in the success cases. And also we have this kind of token also recognize this kind of top failure words. So you can see that for top success cases, those kind of words is we do not see too much kind of patterns. Just regular kind of medication name or some medical terms. And but for the failure cases, we see the clear trend that many of them are numbers, and those kind of number and are high related with the kind of one guess will be that those kind of number calculation even harder for the COD settings and may have bring those kind of more cases. But still, there's ongoing project to explore why this happens. But those kind of patterns will be very interesting to explore. And the third analysis we want to explore that's the we just directly explore that's the error analysis. So for the COT failed cases, what are those error looks like? So here we using two layers of exploration. So one is that we using the LM as judge. That means we using OpenAI O3 model to use a judge model and to assess those kind of error reasons. And then we also have two physicians to manually review this kind of chart performance and have already showed that the O3 has very good performance on the automatic evaluation. So we use this kind of automatic chart to evaluate the three error sources: hallucination, omission, and incompleteness. Hallucination means that have will generate some kind of non-fact information. The things has not been included in the inputs but just fabricate those kind of facts during their reasoning. And omission means that have a missing kind of a many kind of the important information in the input information. So just ignore those kind of important clues. Incomplete means that have when they do the prediction or the reasoning chain is not complete. So that'll be the three kind of main problems. So we explore four different kind of TVRM and to assess the distribution of the errors. So here, those kind of we see the GPT-4 is 7.7% of errors in the hallucination, and for omission increments they are quite rare. For Kun and the Llama 3, they are both are very rare, but they have a higher kind of hallucination rates on these two models. For the mini Llama, this will be fine-tuned for medical data on Llama 2 version. They have a red similar kind of hallucination rate compared with Kun and Llama but have a much higher kind of problem errors on omission and companies compared with other models. So that'll be the our initial exploration on why the COT fails. So here I also want to share some kind of interesting exploration on the stigma language on the EHR output. So the stigma language has been identified as kind of discrimination language against those kind of patient identified group of people as from NIDA has been defined as kind of settings. But general settings they have a lot of kind of offensive language or in respect language to the patient. So alcohol abuser, the patient needs to clean himself, etc. The consequence of this kind of stigma language will reduce the willingness to seek treatment for the patient and have stereotype and have other negative effects. This kind of stigma has already been widely explored on EHR nodes. Many studies has already explored that. They find that stigma language is quite popular in EHR nodes, and but the stigma language identification in the LM generate outputs is understudied. We do not see too much kind of exploration on this kind of direction. But with those kind of generative AI kind of tools, ambient those kind of AI tools have become increasingly integrated into EHR system. They have many more and more kind of EHR nodes have just generated by AI and copy paste by the physician. And so this has become an urgent patient safety issue. We want to explore so AI generating and output as these also includes kind of similar or well they just enlarge the kind of rate of similar language. So we base our experiment we do some specific analysis. So the general settings is that we only here this experiment only explore the English task because we only have include or only have developed those stigma language identification tool on English dataset. We don't have the tool for other kind of language. Will be our first future work. But here we based on our 87 average data, we select the 35 English tasks and we still get those kind of 95 models. And we have a rule-based stigma language identification tool which has already been validated by physicians. And then we'll do several evaluation settings, such as compare different kind of models, what's the stigma rate difference across different kind of model, different kind of task, different kind of input output, and different kind of predictions. So here will be the general kind of distribution of the model. So the each cell represents a combination of model and tasks. We have 35 tasks, 35 row, and 95 columns. So the general distribution is that we have from 0% to 34% across all the model task pairs. So here you can see those by trend M2 model. Then on some mimic IV CDM tasks, they can reach 34 more than 34% of stigma rate. That means every three output they have one stigma text. So it's not neglectable. Even for those commercial models, GPT-4o, they have a rate from 0% to 12%. For sometimes they have even have 12% of stigma language. In average, you have more than 2% of stigma rate. So here we compare different model across groups. So such as the reasoning and the non-reasoning model. So the reasoning model generally have a higher rate of schema language. That's not surprised because reasoning model normally they have generally longer kind of reasoning text compared with the non-reasoning settings. So it's have more likely to have includes kind of schema text. For medical and the general set models, they have the medical model normally have a lower schema rate compared with the general model. One reason maybe that the medical model was trained, fine-tuned with the many EHR kind of data, which although they still include stigma, but the rate may be lower than what we see from general context. And we compare the open source and proprietary model. They have a proprietary model have a lower stigma rate compared with the open source model. So the reason maybe that the big companies have their own kind of big teams for this kind of the red teams to do some kind of safety alignment and end before they release to the public. So they have a kind of an additional kind of safety layer to have make those stigma language rate lower, but they still have a more than 1.5% of stigma rate for this kind of model. So here we explore the different model, the stigma rate distribution across the input text, the type of input nodes. So we see the discharge summary. If input the input node is discharge summary, they have highest kind of rate of output stigma rate, 3.5% of rate. But for the radiology report, they have a very, very rare kind of as the input, they have very rare kind of stigma text mentions. And here is the interesting study we want to explore that because the input have EHR nodes, output generate text. Well, our kind of interesting point is that for the some input, for the EHR input, they may already include schema language, and with as to process this kind of input, where the output kind of rate will be even larger than the input or lower than the input. So then we can see will will enlarge the rate of the schema rate or not. So here we realize the input and output kind of schema rate comparison. The x-axis represent the input schema rate, y represent output schema rate. So for this dash line, that means if the dot under this kind of dash line, that means the output text schema rate is lower than the input rate. So the LM can be reduce the schema rate when processing the kind of text. But for the dots that over than this kind of line, that means those kind of model, the inputs kind of schema rate is lower, but is lower than output schema rate. That means when LM process kind of text, they can enlarge the rate of schema text. So we see there's quite a plenty of kind of model and tasks can enlarge the kind of schema rate across over this input text. So those be the kind of initial, those be ongoing project. We have a manuscript in preparation, and but be some kind of very interesting observation we see from this analysis. So also will be the two additional kind of analysis based on the benchmark we have, and to summarize this comprehension of work is that we have built in the largest and most comprehensive benchmarks, and those benchmarks built purely on real-world clinical data. And our benchmark is multilingual; it covers 9 languages, and transparently have all the detailed prompt settings and evaluation code, all those kind of things are publicly available. And the largest scale of data we have, to our knowledge, is the largest kind of event benchmark and the most diverse benchmark we have seen, and have a large number of experiments and for this kind of settings. I have a leaderboard as we showed before, and to have direct comparison with different kind of settings. And we do have some interesting observation, the open source model with commercial model, also COT will analyze the reason of COT failures and also explore some kind of safety of output. And our hope is that we want to have this kind of benchmark serve as an authentic foundation for the evaluation of LLMs and include this kind of dual release model. We have a ongoing experiment to include this kind of dual release model and to update this kind of leaderboard once we have completed the evaluation of the new model. So those we join work with many kind of teams, as many from Harvard Medical School, Mass General Brigham, and we also collaborate with MIT, Stanford, Mayo, and the UIUC. And we also welcome new data. You have some interesting data from clinical. Well, happy to connect, and we can include some data in our benchmark. And yeah, I'm happy to take any questions. Thank you.
Thank you so much, Dr. Yang. Perfect timing. We have about 7 minutes for questions. And anyone who has question, feel free to raise your hand or just speak. Hi, Florent.
Yes, thank you for this amazing talk. I had a question about the benchmark that, in the tasks that are included in your data set, in benchmark. So I was wondering, because I feel like there is a lot of, name entity recognition, text classification, etc. But I was wondering how you tend to, include more like clinical reasoning and more complex tasks that can involve, several answers from the LLM for instance, diagnosis, multi-step reasoning, etc. And so if you plan to, if it's already included or if you plan to include in your benchmark, and how does it evolve with the capacities of the LLM, so that, for now, this new benchmark is not saturated, but how it could evolve. And yeah, thank you.
Yeah, thank you very much. Yeah, so we do include many kind of clinical applications. So here we just split them into NLP kind of tasks, but they do have kind of more kind of clinical kind of settings. So just the text classification, we normally they include some kind of tasks for the different diagnoses, and but we just categorize as a NLP task, just regardless of the text classification task. But they do include kind of triage and different diagnoses, those kind of things. But we do not include because those are limited to the data we collect. We are not create the data by ourselves, such that we use the MGB kind of data to do this kind of things. We only rely on the data we have collected. So that would be one limitation. We cannot design, okay, here we see the different diagrams, maybe not too much kind of to task. We will add those kind of, we cannot add those kind of things because we only include the open source tasks we have. But they do include those kind of tasks, that different diagrams, triage, and risk factor phenotype. You can see here, this kind of have a more kind of clinical kind of categorization.
Okay, thank you so much.
Okay. Then you can also scan this kind of thing. Oh, you can just find this website, just search kind of bridge benchmark to find the leaderboard, and it will keep updating this kind of leaderboard. And yeah. Oh, I just forgot to mention we didn't include those kind of isotropic model, and which have been commonly quite become more and more popular, right? Example, coding kind of way, because we cannot find a good kind of HIPAA combines environment to run this kind of experiment. We really want to include this kind of model. We talk with Mayo Clinic and our collaborator. I say they are very expensive to run this kind of model in their setting. I don't know why, but yeah, we're happy to just kind of have know some kind of pace that can run this kind of isotropic model in the HIPAA compliance environment.
I think it's very surprising that the medical models or the clinical LMs doesn't arrive the first on the leaderboard. So, do
Yeah,
you
the
have?
medical substitute model, right?
Yes. you have
Yes.
any insights about that, or just they are
Yeah, so
older?
I think because we also have other ongoing projects to fine-tune those kind of existing medical tests, such as we fine-tune MGB EHR nodes, and we see the performance have good performance on different tasks. But I guess one reason is that if the really fine-tune on EHR data, it's really hard to release to public. You can train them and you cannot, and such as the mean number, right? They fine-tune on the mimic data, but they not fine-tune from the year or their own kind of EHR. The Gatatron, right? They fine-tune on unit for that they say, but they cannot release the full model to the public. So that'd be one reason. Another reason is that so the reason is that the scale of model trained on real EHR nodes is hard to be released. Another one is that the academia research group, or they are normally trained, spend maybe months to train the model on the old version of base models and fine-tune on those base models. Such as MiNAMA, they fine-tune on NAMA 2, and then NAMA 3 release, and they have a new Queen model release. They are much better. Those base models are much better than the previous old model. So when they release kind of models, kind of commercial big companies already release the new version, which much better than the original base model. So that will also be kind of another reason. So academic group is hard to compete with some big companies.
Okay, thank you. And would you say it's a lack of, privacy evaluation and security guarantees that there won't be any leakage, or just
You
very
mean
hard
you
to?
mean release the model that trained on your specific EHR system, right? Yes,
Yes.
it's really hard. We have explored this kind of topic for a long time. We tried with the MGB They approved, actually approved our kind of, so we say we were going to release our model train on MGB node, but we still cannot, are not there to release because we may need to talk with some research or lawyer in MGB system to get a final approval. Even RB approval is not enough to allow us to release. There is it's hard to guarantee because we say we're using de-identification tool to identify those kind of nodes, but it's not guaranteed that the de-identification tool can de-identify 100%. Even one or two information HIPAA this kind of PHI information left in the corpus, we cannot guarantee it cannot be leaked. So it's really hard.
Okay, thank you so much.